This is part 5 of the Chapter 5 summary for the Deep Learning book, authored by Ian Goodfellow and others as presented on screen here. The focus of this section is on Bayesian statistics. Probability in the abstract sense is often considered from two different perspectives, the frequentist and the Bayesian. Lots of different discussions and examples of the differences between these perspectives can be found online, while the description from the textbook is provided on this slide. The authors suggest that a primary difference is that the Bayesian approach uses probability to reflect degrees of certainty in the knowledge of the state of something, whereas the frequentist belief can only provide the record of outcomes from a population. The critical idea is that the frequentist understands the parameter being estimated as having some constant but unknown and non-random value, with the estimator that's based on a sample from that distribution being random. On the other hand, the Bayesian considers the unknown true variable as being uncertain and thus random, allowing for probabilistic statements about that value to be made. I find that this difference is the most straightforward to understand and consider. For a strict frequentist, the definition of probability does not allow for assigning probabilities to non-repeatable events. The definition of probability is that the proportion of outcomes observed to take on a given value. This is fundamentally different from Bayesian probability, which exists in the framework of non-repeatable events. Given that the Bayesian considers the parameter in question as a random variable, it's described by a probability distribution. This is what's called the prior probability distribution, or just the prior. It's called the prior because it is the distribution we assign to the random variable before observing any data. With each data observation, Bayes' theorem can be used to update the prior distribution, creating a posterior distribution. And with every other new piece of data, the posterior distribution can then be reused as the new prior distribution, evolving once again to create a new posterior. Iteratively repeating this process is how to perform Bayesian parameter estimation, or inference. There's a link in the description to a great website blog post showing an example computation of this estimation for coin flipping. An initial prior distribution is often determined arbitrarily or subjectively, which is a critique of the Bayesian approach. This allows for creating prior distributions that set a preference for simpler solutions, such as a solution with smaller magnitude coefficients. That's the weight decay solution we saw earlier. Prior distributions are usually started off as being very broad, so as not to bias data too much in any one direction. An important distinction between frequentist and Bayesian methods is that a frequentist estimate is a point estimate, whereas the Bayesian estimate for a parameter is instead given by the entire distribution. While the frequentist accounts for uncertainty using variance, the Bayesian perspective is to integrate over the distribution to evaluate uncertainty. A second important difference is that the Bayesian method shifts probability mass density according to the prior distribution. As discussed in the last video, we hope to have some guiding principle to construct a good estimator. For the frequentist approach, that was the maximum likelihood estimation method. A similar strategy applies to the Bayesian approach as well. That is the maximum a posteriori inference, or MAP, M-A-P. The map creates a point estimate, which can be useful in some circumstances to allow for a solution where one could not be reached otherwise. The equation reads that we want to select the parameters theta that maximizes the probability of the parameters being theta, given the data sample set x. On the right is the standard log likelihood and the prior distribution. As has been seen before, taking the logarithm prevents the risk of arithmetic underflow. The nature in which map inference incorporates previous underlying knowledge through the a priori distribution makes it yield similar results to some other strategies. For example, the text shows that applying a Gaussian prior on the weights of a linear regression model creates a process equivalent to weight decay, a regularization method discussed previously. This doesn't hold as a truism for all strategies, however. The takeaway is that map inference can be leveraged to create complicated but interpretable regularization terms. That's all for this video. In the next one, we're moving on to a deeper look at supervised learning in the Introduction to Machine Learning in the Deep Learning book.